Hi everybody. So here we have an exam question on modelling with differential equations. We're told that a tank at a chemical plant has a capacity of 250 litres and that the tank initially contains 100 litres of pure water. So I'm going to highlight this information because that's important. Salt water enters the tank at a rate of 3 litres per minute, and each litre of salt water entering the tank contains 1 gram of salt. It is assumed that the salt water mixes instantly with the contents of a tank upon entry, and at the instant when the salt water begins to enter the tank, a valve is opened at the bottom of the tank and the solution in the tank flows out at a rate of 2 litres per minute. So that's important. Given that there are S grams of salt in the tank after t minutes, I need to remember that t is in minutes. For part A, shown that the situation can be modelled by this differential equation. Okay, so if we're looking at S grams of salt and we want to work out ds by dt, which is how this changes with respect to time, then we need to find the rate at which this is going in and the rate at which it's coming out. Because ds by dt will be the rate in minus the rate out. And we're told here that salt enters the tank at 3 litres every minute and that each litre contains 1 gram of salt. So the rate going in will be 3 grams every minute, and that when the valve is opened, the solution flows out at a rate of 2 litres per minute. But the solution flowing out will be a mixture of pure water and salt. So what we need to find is the concentration of the salt in the water. This will be the amount of salt divided by the total amount of water. And because we've got 3 litres going in and 2 litres coming out, there'll be an increase of 1 litre every minute. We start with 100 litres and we're adding 1 litre which contains 1 gram every minute. So the rate out will be the amount of salt in the solution at any point in time divided by the total amount of liquid in the tank at any time. And this will flow out at a rate of 2 grams per minute. So we can simplify this and we get 2s over 100 plus t. So now ds by dt will be the rate in 3, this 3 grams per minute, minus the rate out. And this is exactly what we were asked to show. Okay? So for part B, hence find the number of grams in the tank after 10 minutes. So now we need to derive an equation for S by solving this differential equation. And you can tell by inspection that this is the reverse product rule. So we need to move this term to the left-hand side. So if we say, for part B, ds by dt plus s multiplied by 2 over 100 plus t. So I'll split this up because when you differentiate the s, you get ds by dt, and then we can use this as our integrating factor, and this will equal 3. So to work out our integrating factor, we can use the equation where e is raised to a power of p integrated with respect to t. And this p term becomes 2 over 100 plus t. So if we integrate 2 over 100 plus t with respect to t, we can pull the 2 out in front, so this becomes 2, and then the integral of 100 plus t. When you integrate this, we get 2 times the natural log of 100 plus t. Okay? So now we'll substitute this back into this power, so we get e, and because we're dealing with logs, we can move this 2 up to a power, so this becomes e to the power of a natural log of 100 plus t squared. And then we know that this e and natural log will cancel. So our integrating factor becomes 100 plus t all squared. And then we need to multiply every term in this equation by this. So we get ds by dt, lots of 100 plus t squared plus 100 plus t squared times 2s over 100 plus t. We'll just move this down, and this will equal 3 lots of 100 plus t squared. And now you can see that this will cancel with this one. So now we can integrate both sides with respect to t. And this becomes s multiplied by 100 plus t squared will equal the integral of 3 multiplied by 100 plus t all squared. Now we can evaluate this integral. We'll pull the 3 out in front, and we can integrate this using the reverse chain rule. So if we let y equal 100 plus t cubed, we'll find dy by dt, which will give us 3 lots of 100 plus t squared. So we need this to look like our integral, which means we need to scale this by dividing this by 3. So we divide the y by 3 as well. And by dividing both sides by 3, you can see that this multiplication will go. So we'll get s lots of 100 plus t squared will equal 100 plus t cubed plus the constant term. Now I can work out this constant using the initial conditions, which we're told here. The tank initially contains 100 litres of pure water. So this means when t equals 0, s will equal 0. So if we go back to our equation, I'm also going to divide both sides by this term, because you can see it will cancel with less. So s will equal 100 plus t plus c over 100 plus t squared. And then t will equal 0, s will equal 0. We'll substitute both of these into here. So 0 will equal 100 plus c over 100 squared. We'll move this 100 to the left-hand side. So negative 100 will equal c over 100 squared. So c will equal minus 10 to the 6. And now we can put this constant term back into our equation here. So s will equal 100 plus t minus 10 to the 6 over 100 plus t squared. If we go back to the initial question, find the number of grams of salt in the tank after 10 minutes. So we'll substitute in that t equals 10. So s will equal 110 minus 10 to the 6 over 110 squared. We can work this out on our calculators, and we get s will equal 27.35 grams. Okay, so that's part B. We go back to our question. When concentration of the salt in the tank reaches 0.9 grams per litre, the valve at the bottom of the tank must be closed. Find the nearest minute when the valve would need to be closed. So if we look back up here, we said that this was the concentration of salt in the tank at any given time. So we need to make this equal the 0.9. So if we say then that the concentration will equal s over 100 plus t, and we told in the question that this equals 0.9, we can move this denominator to the left-hand side. So therefore, 0.9 lots of 100 plus t will equal s. So we get 90 plus 0.9t will equal s. And then we can use this value for s into our equation to find out this time. So if we put all of this into here, we'll get 90 plus 0.9t will equal 100 plus t minus 10 to the 6 over 100 plus t squared. So now we can move this term to the left-hand side and move these to the right-hand side so we can collect the like terms over here. So therefore, we get 10 to the 6 over 100 plus t all squared will equal the 100 minus the 90 and the 1 minus the 0.9. And then can you see that we can factor out the 0.1 on this side, so we have an expression looking like this. So we'll have 0.1 multiplied by 100 plus t. And then we can move this denominator to the right-hand side, so we get 100 plus t to the power of 3. We'll move this 0.1 to the left-hand side, so we get 10 to the 7, and then we'll take the cube root of both sides. So therefore we get 215.4 will equal 100 plus t, so t must equal 115.4. And I think we were asked to the nearest minute. Yeah. So this will give us t is equal to 115 minutes. Okay? And the next part, evaluate the model. Well, the model is only valid until the valve is closed. So we'll say that the model is good when t is between 0 to 115, but not suitable when t is greater than that. Okay?